Okay, so here we're going to focus on turn our attention to surfaces and how friction affects those surfaces. So this section we're going to kind of break up into a bunch of videos because we're going to look at the different scenarios possible. So with Newton's second law problems, we're always going to make the assumption at this point in time that the objects are going to slide as opposed to roll. Rolling is going to be taken care of when we do talk about rotational motion, okay? Albeit that rolling friction is a lot less than sliding friction between the two types of sliding friction, which are kinetic and static. And we'll get into that here in another video or so, okay? Now, in the long run, when we talk about surfaces, right, we're going to break them down into two categories, right? The first category is when the surface is frictionless. Okay, and that's going to be important because really, when you talk about a frictionless surface, you're only going to look in the x direction. Right? There is no factor of the y direction because we don't have to worry about the normal force, which is one of the big factors for friction. And then the second category is now when you do encounter friction. So you're going to encounter a surface with friction. Okay, which means then you're going to have to account for the x and y directions. Okay, because there's going to be something in the vertical direction that you need in the horizontal direction. And so now we're going to look at kind of frictionless surfaces, frictionless horizontal surface, because one of the last videos in this section will end up being what happens now when we incline the surface. So we're going to just go look at, tables, all right, and flat ground and so forth. But the key thing is what you need to do is, right, follow the procedure that we've been describing throughout these videos on Newton's second law, right? Draw, sum, solve, okay? And so here's the first example. So no friction, right? So this is a no friction problem. The 4.60 kilogram sled is pulled across a smooth ice surface. And this is, if it's not explicitly stated that it's a frictionless surface, if you see something along the lines of smooth ice or icy, then we're talking frictionless, okay? So the force acting on the sled is a magnitude of 6.20 newtons and points in a direction of 35 degrees above the horizontal. Now, what is the acceleration of the sled, okay? So we're going to follow our process, right? Draw, sum, solve. So we're going to draw our free body diagram. So here's our sled. The first force you always draw on your free body diagram is the weight, because all objects have mass, right? Which means they all have weight. What counteracts or balances the weight? The normal force, okay? And then we have this force that is directed, has a magnitude of 6.20 newtons, right? Measured from the horizontal of 35 degrees. We're just going to call this F for right now, and then we're going to have to kind of break this apart, okay, into components. Now, I mentioned that with a frictionless surface, right, you're probably going to ignore the, you will ignore the y direction, okay, and this is the case, right? So what you would have to do is break that force vector into components. So you would say Fx equals F cosine theta, and Fy equals F sine theta. All right. Now you can find the number for those. You can also just simply hold off and plug those values in later, because on the AP test they like these algebraic expression type questions. So again, my recommendation: do as much of the algebra as you can before you plug in numbers, because you never know what they're going to ask you on test day. All right. So we're going to sum the forces in the x and y directions. Now, like I said before, you really don't have to worry about the y direction here. I'm going to just do it for practice, okay? So the sum of the forces in the y direction is going to be 0. And so the sum of the forces will be Fn up, Fy up, Fg down, right? And it's going to be equal to 0. In the x direction, you're going to have Fx positive, and that's the only force acting in the x direction, okay? And so you're going to have the x component of that force is what's causing the acceleration, right? And so here's our line. Remember, anything above the line is physics. Really, anything below the line is math, right? And not necessarily difficult math, but just simply algebra 1. Okay, so our answer is going to lie here in the horizontal direction. So all I'm going to do is divide the mass over. So I'm going to take the x component of that force and divide it by the mass. Okay, and so let me change colors because we're going to run into the red there. And so we're going to do F cosine theta divided by m. And now I can plug in my numbers. So it's going to be 6.20 cosine 35 divided by 4.60. Okay, and that's going to give me the acceleration of this of this sled. So 6.20 cosine 35. Always make sure your calculator is in degrees. And so our acceleration will be 1.10 meters per second squared. Okay, and this will be a positive because we assume our direction of motion would be positive. Okay. All right, so now the next question, very similar, but then we're going to kind of have this force that slows it down. I say this is without friction, and we haven't spoken about friction, but in actuality, this force that slows it down is friction. Okay, but again, because they give us the value, we don't have to do anything in the horizontal or in the vertical direction. Okay, so if we follow our steps, draw, right? So we're gonna look at that point of interaction there, right, on our sled. So we're gonna have teenager 1 is gonna be so we got teenager 1 pulling up and to the left. We have teenager 2 pulling down and to the left. And then we have this 57 Newton force, okay, to the right. And so there's our free body diagram. This is also very simple. They tell us the direction of the acceleration. And what I'm going to do is say, okay, the positive direction is going to be to the left, because if you look in the picture, they tell us that we're going to accelerate to the left. And I just want to keep that idea of my positive always points in the direction of my motion. Okay, and so we're going to have to break down the x or the force vectors again. So Fx equals F cosine theta, Fy equals F sine theta. The good thing though is, like, if you were to look at, since they're equal in magnitude but essentially opposite directions, the y components would essentially cancel each other out. Okay, so we do our summing. Sum of the forces in the y direction equals 0. And so the only thing you have acting in the y would be F1y minus F2y, right, equals 0. Okay, again, I'm just doing the y direction more for practice. So sum of the forces in the x direction is max. Okay, and so we have F1x plus F2x minus this 57 Newton force times, instead of equal to max. And so our acceleration is just going to be F1x plus F2x minus 57 divided by our mass. Okay, one thing about the mass, you have to be careful. They give you to you, I don't think I ever officially read the question, but you have a 19 kilogram child riding a 3.7 kilogram sled being pulled by teenagers, both of them exerting a 55 Newton force at 35 degrees in the direction of motion. And then we have the 57 Newton force going opposite direction, and we're finding the acceleration of the sled and child. So you guys have to, because we're looking for the acceleration of both, this mass is actually going to be what we'll call total mass. Okay, and so now I'm just going to plug in right? F1 cosine theta plus F2 cosine theta minus 57 over total mass. Okay, so it's going to be 55 cosine 35 plus 55 sine 35 minus 57 divided by 22.7, which is our total mass. Okay, so then we're going to plug all this stuff in. So you got an acceleration of positive 1.46 meters per second squared. Okay, so this is when we do not encounter friction. Okay, although albeit in here in the second example, we did have this 57 Newton force that opposes, but we haven't officially defined what friction was. And so that's going to be in our next video.